Okay, what is up, guys? So we've done a lot of stuff already with kind of like functions, strings, how to create a class, methods within that class, object-oriented programming. So we've done a lot of stuff with Python in terms of what you'll need to develop a neural network. But before I get into actually coding in a neural network with Python, I kind of have to give you a little kind of introduction in terms of what is a neural network, what is the kind of like the conceptual, the history to it, what is it actually trying to do. So this is what this session is about. Very short session in terms of just some of the neural network fundamentals, and this is not going to go into any great detail. If you want to kind of like great detail course, then you'll need to buy a neural network introduction book, which will basically go into much greater detail. But I'm certainly going to kind of touch on some of the mathematics and some of the general principles in this. So this is the absolute bare bones, and I'll expand on some of these concepts then later as and when they're needed. So let's continue and get into what is a perceptron. So perceptron was one of the very first forms, I guess, of neural nets that you can which were created. So the idea was there was a node and it was a binary output. Binary means either 1 or 0, true or false. So let's say it was trying to detect whether an image was a dog. Maybe these were certain pixels of the dog, and this was basically a pattern image recognizer, and the output would be either 1 or 0, either a true or false. Is it a dog or isn't it a dog? So again, this is the most simple form of a neural network. In fact, it's not even a neural network because it's not networked to anything. It's a single node, it's a single neuron. But this is where neural nets started, so I thought I'd kind of introduce you to the perceptron first. This was created in 1958 by Frank Rossblatt, I believe, and it was funded by the Navy. So obviously the military had some kind of reason to think that this gave them some kind of advantage. Otherwise they wouldn't be funding it. So that was a perceptron. Let's move on to networks and how this is kind of comparable to real neurons. So the top picture here, this is a very simple schematic diagram of an actual neuron. As you can see, it's got that's where the cell is, the cell body and the nucleus. So that's like we've got many cells in the body. We all have a cell body and nucleus, and within that it'll have its usual biochemical parts that you might be familiar with, like an energy source and whatnot. It's also got things called dendrites. Dendrites are little connectors which connect onto other axon terminals. So this is connected to other neurons in a big vast network. So this is called the axon. So when this is stimulated sufficiently, you get something called an action potential, and it's basically a volt of electricity across the axon body. It's actually electrochemical. I'm not going to go into the kind of polarization. We can do that in another session, in a more detailed session. But that carries across the axon to the axon terminals, and each one of these terminals then are connected to dendrites on another cell. So this is how networks of neurons are activated and fired. When enough of them are fired, something will happen. So you could stimulate an arm movement by literally putting an electrode in terms of the motor center and delivering a small impulse of electricity which will fire a whole bunch of neurons. I might show you some videos and things in relation to that in another kind of more biologically related session, but that's the basic idea of how a real neuron works. And the computer scientists have kind of constructed something that is based on this. So it doesn't obviously have a electrochemical, doesn't have an action potential. It's using pure mathematics. So there's a summation, there's some inputs, there's a summation function, and then there's an output. So it's not the same thing, but it's kind of inspired by how real cells work, and similarly this will be connected to other neurons, just like this will be connected to other neurons. And in some ways these are like the axons. These are like the axon terminals here. This is like the axon here. This is like the cell body, and these are like the dendrites connected to other neurons. So, but it's a very loose analogy to an actual real neuron. So don't think of it as or it is a neuron. It's trying to simulate a neuron. It is not. It's just inspired by that. Okay, so let's move on to the next slide. The next slide is this is just a little bit more detail. This is the neural action potential. So when enough other neurons are firing action potentials towards this neuron, a threshold is reached, and then this one fires, and other ones fire, and that's how behaviors are formed. So let's say you had there was a threat, a predator was in your presence, and you had to make a decision, either stay calm or run. Well, something like a threat would cause enough stimulation for a lot of these action potentials to fire off and set off other potential action potentials in other neurons, which would basically then send information down to your muscles to escape the bear. That's a very, very, very simple kind of example, but that's essentially what's happening. All behavior and thoughts are coming from the brain. And influenced by kind of like the endocrine system from the body. Again, I haven't got enough time to go into how all these kind of functions work in a simple neural network session, but that's the basic idea. And just if you do want to read about this stuff, you'll find out there's a lot of depolarizing and polarizing with various chemicals and calciums and what along the actual neurons. So you can read up further about that in other text if you're interested. So let me go on to the next slide. So just like a neuron fires, a artificial neuron in a neural network also has an activation. So I just showed you the activation potential firing with the electrical signal. And I said that has to cross some kind of threshold, has to be stimulated to a certain degree. Well, so do artificial neurons. And there's been a lot of kind of discussion in terms of how, what kind of function we need to set in order for these things to fire. Is it going to be a simple binary on-off, or is it going to be a more smoother, like sigmoid function? There's a whole bunch of functions. I'm going to do a whole separate session on functions, activation functions. There's a whole bunch of mathematics behind this, but in this very first session, we're just not going to go there because it's just too complicated for the very first session. So just be aware there's something called an activation function, and it's kind of similar to how your neuron fires, the action potential. Now, what is the network actually trying to do? I mean, so I mentioned, like, the perceptron tries to take a bunch of pixels and say, is this particular image? Well, the neural network's actually very, very good at recognizing symbols and images. Pattern recognition is actually very, very good. These networks are very good for this kind of thing. So you might have like symbols not like created in your regular font scales on Word, but something like the kind of handwritten. So you might have lots of different 2s there, and every person in the world will write a 2 or a 5 slightly differently. You'll have your own, and even if you write it again and again, each time you write it's going to be slightly different. You'll never replicate the number exactly twice. So the network has to basically train on a bunch of data, and once it trains on data, it's then given a new set of data, and it's asked how, what are these items based on the training you've received. So that's the very basic principle. So these are like the inputs, the initial inputs to a network. You train it, and then you test it against other real data. and then you can see how successful it is. So that's the basic principles of what the neural network is doing. It can do a lot more than that. They use it in like driverless cars, the autonomous vehicles and stuff to identify certain roads and things like that. I might get into more complex examples, but for this basic session, that's what it's trying to do. It's kind of a pattern recognizer. The mathematics behind it, what you need to know, there's a lot of maths behind it. Like say the activation function, that's got a whole bunch of maths behind it. But I just wanted to show you the kind of general maths about how your inputs, weights, and your bias work. So this is a one node. So this is a perceptron, but the difference between a perceptron and a let's say a neural network is a network would just have more of these nodes. There'd just be more calculations. But just to simplify, I've just used one node there, and all it's saying is your activation. Your activation is basically your individual weights. And that basically means weights. So whenever you see this sign, it means sum of your weights from 1 to n. That basically just means your full set. So you could specify that 1 to 10. So only using 10 weights. But it's basically 1 to n means 1 to the nth. The nth means however far it goes. It could be 10,000. It could be 100,000. It doesn't matter. N would represent the last one, wn. So this is why it's got 3 dots here. So it's not specifying how many weights you need and how many inputs you need. So it's basically the sum of weights times the inputs, so weights times inputs, plus a bias function. So each node has a bias function. And for this first part, don't worry why we need a bias or why we need weights. I'm just trying to show you the basic mathematics. I'm going to go back to some of these things and add to your knowledge as we go on. So there's your inputs. That could be your numbers, whatever inputs. It'll be encoded in terms of a numerical form, and then which represent the patterns. And then you've got certain weights attributed to the inputs, and that goes to a particular node, which then feeds to your activation. So yes, no, is this a dog, or yes, no, is this the number 2? So let's say your initial activation numbers were 0.2, 0.4, 0.3. Again, I've just arbitrarily made these numbers. I'll go into this in more detail at another session. These are your weights. Your weights are basically how strong the relation is. So this weight here is stronger, has got a stronger connection to the node than these two. So this will have more influence on this node than these two. And this is your bias term, which is just set, and I'll go into that in more detail. And this is your activation. This is your output. And it's simply, to do this formula, it's simply, remember, it's basically saying 0.2 times 0.1. That's what it means. Weight times x. X is your activation functions. These are your W, your weights. So 0.2 times 0.1 plus, because remember it's a summation of the next one, which is 0.4 times 0.1 plus, because again it's a summation, and there's the times there, weight times x, 0.3 times 0.2, and this is your final bias term, the 1. So you do these first and then you plus it by 1 at the end. So 0.2 times 0.1, I hope I did these multiplications correct, 0.02 plus 0.4 times 0.1 is 0.04 plus 0.3 times 0.2 is 0.06 plus your bias, which is 1. So that will be 0.02 plus 0.04 plus 0.06 would be 0.12 plus 1, which is your answer. Your output, your A, your activation function, will be 1.12. So I hope that maths is kind of easy enough to understand, and I will go through that again to make sure you haven't forgotten, and I'll add things to it. Again, we do have to still do the activation, and there's also something called gradient descent in terms of its back propagation. Those are too complex at this stage, so there is some more mathematics to it, but that's basically how a network is working. So again, if you had more nodes, this is exactly the same as before, but before I just had the one node. Now I've got 2, 3, and a second layer. 1, 2, 3, 4. So I've got 4, 5, 6, 7 in total. There's your output there. So all of a sudden I've got a 2-layer network, whereas before I had a single perceptron, a single node, and an outcome. Now I've got 3 nodes for my first and 4 for the second. So you'd have to do that formula you saw in the last slide, and you'd have to repeat it, and I'll show you how to do that. But it just, obviously with the Python software it can be done very, very quickly, but I'll show you how to do that in a very, very quick way. But it's nothing complicated, it's just repetition. You've basically got to do it once for this one, which we just did in the last slide, and then do it again for this one, and do it again for this one. And then we've got to work out the outcomes, and input the outcome from this one that we did last time, and then input it into this one, and do it again, the outcome for this one, and input it into this one. Well, basically the outcome, you have to repeat it for each one of these connections. It's basically this is creating an input for each of these nodes, this one's creating an input for each of these nodes, and this one's creating an input for each of these nodes, and then you get your outcome. So it becomes very complicated, but it's not difficult. It just means repetition of the same formulas, and these can become very deep. These are deep networks, and these are the kind of things that you're using now to DeepMind. They're using also like reinforcement learning and OpenAI, but they're using like deep networks plus other kind of algorithms like reinforcement learning to learn how to play very, very complex games. So the more complexity in your inputs, and the more kind of behavioral activations you want at the end, you need these to have several layers to be able to take in a lot of information. So these more complex, deep layers, they weren't possible back in the the 50s and 60s because we didn't have the computational power. But now there's renewed interest in neural networks because we do have all these. They use not CPUs, not your general CPUs, but your GPU, your graphical processing unit. I think they're called tensor cores. They have lots of tensor cores which can take huge bits of information and process them. So a task that might have taken weeks or months before can be done in just a few minutes now. So they're becoming the applications of these now is you don't need supercomputers to do small processes. You can actually use these kind of applications on a high-powered desktop computer. With obviously with a tensor cores on your graphical processor. You don't want to just use a CPU. You want a proper machine learning machine. Anyway, that's the basic idea. The last thing I'm going to mention is I haven't mentioned everything. Of course, there's a learning. So the way that the network works, it backpropagates, or some of them. The one I'm going to show you've got feed forward, but the ones I'm going to show you is going to be a backpropagation. So it kind of learns, and it's trying to minimize its error. So it does this. It's trying to find the path of least resistance to gradient descent. So it's trying to reduce the error function and trying to, you don't want it overfitting. If it overfits, it can't generalize to other data, but you want it, you don't want the error to be too big either because it's not fitting properly to the data you've got. So there's always a trade-off there. And again, it's too complicated for this very simple introductory session, but I think I've given you enough now, so we can now move on to actually programming a very simple neural network, and I'll then put in more complexity to it, and I'll add additional Python sessions where you need to build on that basic knowledge that you already have. So anyway, I hope you like that, guys. Please click subscribe, like and subscribe if you enjoyed this, and I will see you in the next session. Thank you very much.